In this video, we're going to finish up the concept of standard deviation and kind of what it means. Um, Now, there was a person named Chebyshev who came up with this rule, and it's kind of like what we've been talking about as far as standard deviations representing the likelihood that someone's going to fall within some range of what we consider to be normal or quote unquote average. Um, what he said is we could break this down to a worst case scenario probability or percentage using this formula here, where k represents the number of standard deviations within the mean, or from the mean. So therefore, like for example, if we say k equals 1, then what that means, that was the worst curve I've ever drawn. Okay, let's try that again. There we go, much better. What he is saying is he will guarantee worst case scenario using this formula, the percentage of people or the probability of you finding somebody in that grouping would be 1 minus 1 over 1 squared. So therefore, that would result in 1 minus 1. So therefore, he guarantees 0%. So if you have average here, and you go up 1 standard deviation, and you go down 1 standard deviation, he says that group of people in this area, he guarantees the number of people that actually will fall in that range will be 0. And that makes sense when you draw your picture this way. When you say it's a bimodal distribution, you say you are building a shoe store for the strangest population ever. Only people, one of your modes are people who have size 21 feet, and the other mode is for people who all wear kid sizes, size 6. Okay? So therefore, the average, the mean, would be somewhere in the middle. But if nobody in this town actually has that size shoe because they either are giant feet or itty bitty tiny feet, there's not going to be anybody in the actual average. And this is what he's saying is if you have the worst possible scenario, so unlikely ever, he guarantees nobody will be in there. Make sense? Okay, now that's for 1 standard deviation. Now let's do k equaling 2. What would that be? Well, it's 1 minus 1 over 2 squared. So therefore that results in 1 minus 1 over 4. So that is what? 0.75. So now what does that mean? This guarantees that even with a horrible sample, if you go 2 standard deviations of the mean, 2 standard deviations up, 2 standard deviations down, you are now guaranteed 75% of the population. Do you get the power of that? You can spend very little time on your study, and if you find that your shoes that you want to stock in your shoe store fall within 2 standard deviations of the mean, that makes sense to you. Worst case scenario, 75% of the people who walk into your store, you're going to have their size. Okay? Now, we go k equals 3. And I think you're ready for this. I think you already see where this is going. That would be 1 over 3 squared. So that's 1 minus 1 ninth. So therefore, that is what? 9 ninths minus 1. That's 8 ninths. Or as a decimal, that would be 0.88 repeating. So now you are guaranteed to get 88% of the population. Get the idea? This is what Chebyshev is talking about. So if something mentions Chebyshev's rule or Chebyshev's worst case scenario, best case scenario, or that kind of, well, actually worst case scenario, this is what we're talking about. You say worst case, if you are talking about something that is within 3 standard deviations of the mean, 88% guaranteed. You're going to handle 88% of the people. Get the idea? All right, the other version is called the empirical rule, or some books just call it the rule of 68, 95, 99.7. And there's no formula to it because it's literally 68, 95, 99.7. And I've been using this word a lot. Now you're actually going to see it's actually going to pop up here, and in the next section we're going to formally define it. But the concept of normal, this is actually a mathematical term. And what it describes in very, very short, because we'll talk about the next chapter, but the very, very short idea is bell-shaped, outliers are minimized to the left and to the right. And if what we mean by outliers are people who are not really around the normal, around the mean, but if there are outliers, they're balanced. So for every one person that has gigantic feet, there's one person who has itty bitty tiny feet. And so what this rule says is if you have a normal curve, if your curve is symmetric, it's very nice, it has one mode, then what it says is if you are within 1 standard deviation, so again, from the mean, you're 1 standard deviation up, 1 standard deviation down, that will be 68% of your population. 2 standard deviations of the mean, I think you're already probably figuring it out at this point. If you are within 2 standard deviations of the mean, that's 95% of the population. And of course, now if you haven't put it together yet, this is going to seal the deal. If you are within 3 standard deviations of the mean, now we're at 99.7%. So, and of course, because our curve is symmetric, we can play little games. Like, for example, if I asked what is just the area of this right-hand side, well, if I know both sides add up to 68, then one side, because it's symmetric, has to be half of that. So half of 68 would be 34. So therefore, that's 34, and that's 34. Okay, get the idea? And so then, all right, so be on the lookout for little questions. Another very favorite question to ask is from the mean up, from the average up. What percentage of the population would that be? Well, again, because it's symmetric, that's half your curve, so therefore that would be 50%. Okay, so that's all there is to the rule of, come on, that's all there is to the rule of 68, 95, 99.7. These are 3 key numbers. And this rule can vary a little bit due to the book you are using. So be prepared. They've done some rounding to these numbers, so it may be slightly off by decimals, just depending on the level of accuracy the author is looking for. All right, so that's it for that. So yay! All right, standard deviations. We've kind of talked about them. We're doing awesome. Now we're ready to do almost kind of call it a practice, but we'll put it into this lesson because there is a new trick to this. So there is a new Las Vegas game that pays the players $5 30% of the time. They break even 50% of the time, and the players will lose $3 20% of the time. And if you don't know what break even means, is just $0 changes hands. Whatever they bet, they get it back. So it was like a tie. Okay. Calculate the following. Calculate the expected value of the game. All right. So hopefully you remember from the previous section, expected values. All right, we need a probability distribution table, and I need all my outcomes. Well, I can either win $5, I can break even, or I can lose $3, right? Okay. Now, how often does that occur? Win $5 30% of the time, win $0 50% of the time, and lose $3 20% of the time. Now, does that make sense? Yes, yes, yes. That does add up to 1. So, okay, so far so good. That's every possible outcome. So how do we get the expected value? Well, we take our values and multiply them by their probability, just like we learned in the last lesson. So let me make that a -3 times 0.2. All right, so let's go ahead and calculate that, and I will I'll pull up the calculator here, and we'll go through that. All right, so I just got out of the calculator that this is going to equal 0.9. So test yourself. Do you remember how to interpret that? Is that a percentage? No, no, no. Right, our percentages are all right here in our formula. So expected value is the units that the problem holds. So this is the units that your variables hold. So if these are dollars, this is the units of dollars. So what do we expect? 90 cents to change hands every time we play. And is it win or lose? Well, because it's positive, it's a win. So Vegas doesn't like this game. This would be a great game to play. Play it all day long because you expect to win 90 cents every time you play. All right, so great. Now, let's find the standard deviation of the game. How are we going to do this? Because our standard deviation equation in the calculator, in the calculator, we have to type in a frequency. Or in our formula, let's just go to our formula. Now, this is a population because we're not talking about individual rolls. We're not talking about, I played the game 20 times. What we're talking about is the calculated probabilities. So, therefore, this is, you could kind of think of this as a population. So, our values, we know our expected value. Now, remember, in our formula, the mean, or actually it's the mu, because we're in a population, the mu doesn't mean mean. It means average, right? It's any version of measure of central tendency. So the expected value is absolutely usable here. So what we're going to do is take our first value of $5 and subtract our expected value of 0.9, square it. Then our next one will be what, $0 minus 0.9 squared. And sometimes students try to skip this. They say it's a 0, it doesn't matter. No, it absolutely does, because 0 minus 0.9 squared isn't 0, right? Okay, so then we're going to do our last one here, which is -3 minus 0.9. Yes, you do keep the negative sign. All over. Because it's a population, we need n. So what is our n here? And so what I want to kind of point out is we can, since we know 5 happens 30% of the time, if you kind of think of it like this, say this happened 3 times, 0 happened 5 times, and -3 happens 2 times, then that would give us 10 events, 10 times that we did the game. Because when we add up 3, 5, and 2, that makes 10. We could have very easily also made this 30, 50, and 20 out of 100, or any numbers we choose. But the idea here is this is actually going to give us another version of the formula, which is really kind of easy. It's just the probability of this occurring for each of the values. So instead of having to even write that dividing by n, we can just write it as the probability of that value occurring. You see? And it spits it right out for us. There we go, our standard deviation. Now, the other way I want to point out to do this in the calculator, we go back to stat. We're going to go here and put in our values just like normal. And remember, if you had values in your calculator, arrow up to the L1 column. Do not press delete. You press clear, then hit enter, and it will get rid of the values. So now, what we're going to do, I'm going to type in the values just like normal. My 3 values were positive $5, $0, or -$3. And for my frequency, I now just can type in the probabilities, 0.3, 0.5, and 0.2. So now, when we calculate the standard deviation using our statistics, whoops, don't do that. Go statistics, over to calculate one variable statistics. My list is in L1. Whoops, not alpha. My frequency list is in L2. I hit calculate, and you'll notice there we go. It gives us everything. The expected value, it doesn't use EX, but it does use X bar. And it gives us our 0.9 value for our expected value. Notice it doesn't give us a variance because, why is my brain not working? Standard deviation of a sample, because it knows this is a population. So it only gives us the population value. Ignore the 1, it's just saying it, out of 1 attempt, but that's okay. And there you go. So we have our standard deviation. Our standard deviation is 2.913760457. All right. So now, how we would look at this game if we were a game designer is we'd say, okay, do we have a good game? Well, our mean was 0.9, and that's not good because that means people are winning more than they're losing, and that's not good for a casino. But our standard deviation is 2.9, which means if it was a normal curve, 68% of the time our players are going to be somewhere between $3.8 winning and subtracting, so that take us down to a -2. So does that sound like a fun game? You can't design a game for Las Vegas. Whoops, sorry, that shouldn't be -2 there. The -2 should be right here. There we go. This should still be 2.9. There we go. You can't design a game for Vegas where somebody loses all the time. No one would play. You would just be depressed. So people have to win sometimes. They have to lose sometimes. And so what this is showing you is 68% of the time you're in that range, somewhere between -$2 and positive $3.8. So that's, again, law of large numbers, but again, that's the big idea. You're going to fall in that range. So it's a good game. It's in a good range. They just need to shift this over to the left a little bit so it's in the negatives, but it still will creep into the positives within that first standard deviation. So I hope that makes sense. I hope that helps make sense of kind of how they design games in Vegas. And I like that example because it shows you how you can alter the standard deviation equation to look a little different, but it really is the same thing. All right. I hope this helps. Good luck on the homework, and we'll see you in the next video.